Okay, let's dive right into the 4 different ways. The first thing you need to know to be looking out for is that in each of these ones, we're gonna have 2 different things that we're looking for. The first one is the reaction that's occurring. Like, what reaction are we talking about? Combustion, formation, or something else? And the second part is whether the reaction is exo or endothermic. These need to be able to specify to me those 2 things as well as the energy. So in each of these that I'm going to show you, I'm going to go through those 2 things. We're going to underline the reaction, or at least I will, in red, how it represents the reaction. And then I'm going to underline whether it's exo or endo in green, just to show you that all 4 of these are showing you the exact same information. So let's jump into the first one, molar enthalpy symbols. And this is kind of what we already mentioned with our delta RHM. So for these, you're going to have a delta with an R or a C or something to specify the reaction type. You're going to have your HM, but you also have to specify, like I did in the last video, what that substance is underneath. So you're going to write propane or whatever is being burned or formed or decomposed. It's going to be labeled in that place. So let me do an example of this one. So in your notes, it gives us the example of the combustion of 1 mole of methanol releases 725.9 kilojoules. So my setup here would be delta C, because it's a combustion, HM of methanol, which is CH3OH, and then that equals. And they told us here that 1 mole releases 725.9. So that's 725.9 kilojoules per mole. Remember that this is a delta HM, so it needs to be per mole, not just energy. But I also need to say that it's exothermic because it's a combustion, so I know that that should be a negative value. So in this type of one, the reaction is given to me by saying it's combustion and what is being combusted. So there's the reaction piece. I'm burning something, here's what I'm burning. And the other part, knowing whether it's endo or exothermic, is that symbol right there. Is this losing energy or is it gaining it? Is it exo or endothermic? Okay, that's the first type. All right, let's go to the second one now. Let me just erase this quick. All right, the second one, enthalpy change. And I would write next to this one or underline that part in your notes where it says delta H notation. That's what it's most commonly called, at least in this course. Delta H notation. We're still going to use positive or negative values to indicate exo or endothermic. But now instead of just using symbols to give us the reaction, we're going to write the reaction out. And then to the side, we're going to give it what that enthalpy is. So in your notes, you've got 2 examples. The first one is the formation of water vapor. So you've got hydrogen plus some oxygen gives you water vapor, and then it tells you that that's a negative 241.8. Now the tricky part here, not tricky I guess, but just to be careful of, remember that's a delta H value, not a delta HM. So if you look at the second one, the example that I gave you there, it's the exact same equation, but instead of having 1 hydrogen, half an oxygen, and a water, you have 2 hydrogen, 1 oxygen, and 2 H2Os. So since that's double the amount of stuff, double the logs on the fire, the delta H has also doubled. If this was a delta HM, remember that's universal, that wouldn't change per mole, but this isn't. This is just total energy. So if I change the balancing of the equation, I change that delta H. So in our example, they give us the same thing as we did in the first one. The combustion of 1 mole of methanol releases 725.9 kilojoules. So first thing I have to do is I have to write out the equation balance somehow. So I have methanol, which is CH3OH, It's combustion, so I know I have to have oxygen. Complete combustion, because they don't tell us otherwise. So I'm going to go with carbon dioxide. And we'll assume that this is in an open container, not something sealed. So this is going to be water, gas. Now, I could balance that by saying I've got one carbon, I've got one carbon, I've got 4 H's. So now I have 4 H's if I put a 2 there. And now I have 4 O's over here. The problem being that I have this O right here that's going to throw things off, that single O in the methanol. Now, one way to get around that is to use the fraction method that I kind of introduced you to earlier. So I need 4 oxygen, that's what I've got over here, 4. 2 from the water, 2 from the carbon dioxide. And I've already got 1 in the methanol, so I really only need 3 more. So I could put here 3 halves, because remember oxygen is 2 O's double bonded together, so half of an O2 is just an O, and I need 3 of those. So that's where that comes from. That's one way to balance that out. The other way you could balance that out is to double everything, and you'd get 2 methanol plus 3 oxygen gives me 2 CO2 and 4 water. Now here's where the difference is going to show up, and let me get myself out of the way here so I can show this to you. The difference is going to be the delta H. Remember that delta H is a total number. So because this is 1 mole releases 725.9 kilojoules, in this first reaction here, I only have 1 mole. So that one was going to be a delta H equals negative, oops, sorry about that, negative 725.9 kilojoules. In the second one though, it's not 1 mole. I've doubled the amount of moles of methanol. So that's not 725.9, it's, oh, let me try and do this in my head. I gotta double that, so it's what, 1451.8 kilojoules, if I did that correctly. So in this case, your balancing is gonna have a big impact. If you balance it like the one above there with 1 mole, then the number is that. If you balance it differently with 2 moles, you get a different number. So just be careful of that. Your delta H numbers always have to match how you balanced your equation. All right. Yeah, let's stop there for this one. We'll go through the next 2 in the next video.